In this video, we will continue our examination of Bayes' theorem by applying Bayes' formula. What we'll do in this video is look at some applications, some word problems using Bayes' formula. Oh, let's jump ahead here. Here we go. So here's some word problems. If we have the same setup, 8 red marbles, 5 black marbles, 12 white marbles, and we have a total of 25 marbles. Let's look at some probability with replacement and then without replacement. And when we think about replacement, here's our jar. It's let's call it a bowl instead. So it's, we can't see through it. We can't see what, or the person who's pulling out a marble is doing so with a blindfold. And when they reach in, if the second ball was white, what was the probability that the first one was red? Well, if we replaced that, so if you think about it, the first ball was red, and then we put the red marble back and go for a white marble, do you see that really all we're looking for is what's the probability that the first ball was red? Because that white ball, since it was put back, who cares that that's what we got, right? And all that means is if the second ball was white, all we're really concerned with is that that second ball wasn't red. So in other words, with replacement, it's just what's the probability of getting a red ball? And that's going to be 8 out of 25. If the second ball was black, what's the probability that the first one was white? Well, again, it doesn't matter what happened with that second draw because we put it back. So the probability of getting a white marble is simply going to be 12, because there's 12 white marbles out of the 25. Now let's jump ahead over here to the number 14. We'll come back to 12 and 13, though you might try those on your own without the video. But if we're talking about without replacement, so we know that the second one was white, but what's the probability that the first one was black? Well, what's happening here is that second ball being white, the number of black balls isn't actually affected, right? There's still 5 black balls. But we know that in the future, we're going to get one of those white balls. So the denominator changes to 24. And then if the second, so we have a 5 out of 24. Let me put these percents because the percents sometimes make a little more sense to us. And to get that percent, I'm simply dividing 5 divided by 24 and then converting that to a percent, which means moving the decimal to the left or multiplying by 100. How about the probability, if we know that the second one was black, what's the probability that the first one was white? So the probability of getting that white was 12, because there's 12 marbles, and that first one being black doesn't affect how many white marbles there are. But if we know that in the future we're going to get a black marble, then we could remove one of those black marbles and say that there's only 24 to the denominator. So 50% now. So the probability changes slightly from what it was with replacement, right? Let's try this next one. What's the probability that the second one is black? Or if the second one was black, I'm sorry. Find the probability that the first was red. That's just, again, just going to be the probability of a red because it's with replacements. This is going back to number 12. So the probability of getting red was at 8 out of 25 or 32%. But let's say now without replacing it. So what's the probability that we got a red on our first draw if we already know that in the future we're going to pull out a black marble? In the future, we're going to pull one of those black marbles. So there are now, the chances increased, right? So it's 8 out of 24, just slightly, 33%. Slightly higher than the 32. And then the last example here. The second ball is red. What's the probability the first one was red? Again, since we replaced it, those two draws have no effect on each other. So it's still just the 32%, the 8 out of 25. But if we didn't replace it, this gets a little bit trickier. We know that in the future, we're going to draw one of the red, right? So that means that our first draw, there's not 8, there's only 7. Because we know that the next person who draws is going to get that, one of those red balls, right? But the denominator also decreases. So it's 24. So see how that drops to 29%. That's Bayes' formula. Or we're not really applying the formula yet. We're really applying the theorem. This is Bayes' theorem. Let's look at some other examples that are worded maybe a little differently. So a local university offers a free flu shot to its employees. Of the eligible employees, 75% have the flu shot, 25% don't elect to have the flu shot. Of the employees that take the flu shot, 10% get the flu, and of the employees that don't have the shot, a little higher percent, right? 45% of those get the flu. But wait, they don't tell us how many don't get the flu who had the shot, or how many don't get the flu who didn't have the shot. Well, we can calculate that. Do you see how to do that? Because this has to add up to 100%. So if 10% get the flu, 90% don't. If 45% get the flu, then 55% don't. Going back to applying Bayes' formula, so what's the probability of S given F? What's the probability that if we got the flu, that we had the shot? What's the probability that a person who gets the flu actually took the shot? So we're looking for this 0.75 times 0.10, but in the denominator, we have everyone who had the flu shot, or I'm sorry, everyone who got the flu, whether they had the shot or not. So what this would work out to, it's the probability of those who got the shot and got the flu out of all of those who got the flu. Oh, I'm sorry. I know I'm writing that probability, the P twice. So the probability of those who got the shot and the flu divided by the probability of those who got the flu. So what we're going to do here for the denominator, for the flu, we're going to add both of these. You got the shot and got the flu, added to you didn't get the shot and you still got the flu. So the shot and flu, 0.75 times 0.10, 0.075, divided by 0.75 times 0.0, added to 0.25 times 0.45. So that calculates 0.075 plus 0.1125. So 0.075 over 0.1875. When we divide those, we get a 40%, 0.4 or 40%. So it looks like, what's the probability that a person who gets the flu took the flu shot? It looks like 40% of those who got the flu had the flu shot. And the probability of not getting the flu, given that we already know that they didn't take the probability that a person doesn't get the flu and they don't get the shot. So we know they didn't get the shot. What's the probability they don't get the flu? We're going to have in the numerator the probability of not getting the shot and not getting the flu. Let me go to the new page so we can highlight those just to make sure everyone's clear on that. Let me highlight what we're doing here. So we're looking for the probability of not getting the flu. So it's these two branches. And we are saying that it's no shot and no flu. No shot and no flu. So we have the probability of not getting the shot and still not getting the flu divided by the probability of not getting the flu. So that would be probability of not getting the shot and not getting the flu divided by the sum of both of these. The probability of getting the shot and not getting the flu added to not getting the shot and not getting the flu. So that would add to, what is this, 0.25 times 0.55, 0.1375 divided by 0.675 added to 0.1375. So it looks like our numerator is 0.1375 and our denominator 0.8125. So 0.1692 when we do the dividing. So 16.92%. Let's look at a couple more examples like this. If for 19, an office supply company sells 3 different computers, computer A, B, and C, and based on that brand name, if it's a brand name that you have more confidence in, maybe you'd be less likely to get the warranty. So those who bought computer C, only 20% got the warranty. So I know that 80% didn't get the warranty. Those who bought computer A, 25% got the warranty, so I know that 75% didn't get the warranty, right? And of those who purchased computer B, 40% got the warranty, so 60% didn't get the warranty. What's the probability of A, given we know that they got the warranty? And by the way, could I show you some techniques I use to keep all of this information straight? I actually started by just charting out those numbers. They were easier for me to read from the chart and then put in the tree than they were to read into the problem. Another technique is I've highlighted each piece and then I color coded it on the tree. So you see the 65 is red, the 15 got brand B, etc. So either of those techniques might help you. But the probability of A, given that we already know that they chose a warranty. So we know that the customer purchased a warranty. What's the probability that they had computer A? So that's going to be the probability of the A and warranty divided by the probability of a warranty. So we're going to add the 3 warranty options there, right? So A and warranty it looks like what I'll do is have the probability of the A and warranty is 0.1625. And for the denominator, I'll add the 0.1625 to the 0.06, the 0.04. And that is going to come to 0.1625 divided by 0.2625. So when I divide that, 0.619 or 61.9%. How about the probability of B given W? So we can see we already know that they purchased a warranty. We're trying to determine what was the probability, if you got the warranty, what was the probability that you had chosen computer B? So what's this branch of the tree? I'm going to leave the calculating to you, but just to keep you on track so you can check that you're on the right track, it would be 6/100ths divided by 0.2625, and then you could divide those. But check to make sure you're comfortable with getting the 6/100ths, comfortable adding the three probabilities to get the 0.2625, and then comfortable dividing those. But let's look at this last one, C and W. So we know that they got the warranty. We know we're in one of those branches. What's the probability that, so if we're doing part C, that they had computer C, right? So this branch right here. And if we know it was one of the three branches that had a warranty, so we're going to have 0.04 divided by the sum of 65 times 25 gives us the 1625. 15 times 40 gives us 6. 20 times 20, 20% times 20% gives us 4%. So when we add those up, we get 0.2625, and I'll leave that final calculating to you so that we have enough time for this last example. This is interesting to me because I'm always so interested in politics and who votes for different legislation, or who supports different legislation, and how that affects who you vote for. So here we've got a survey of registered voters, and we know who supports a ban on smoking in public facilities, not a ban on smoking on private property, but in public facilities. 62% said, yeah, that we should ban smoking in public facilities. 30 said, no, we shouldn't ban that. And 8% had no opinion. Now, the next thing we'll look at is who votes for Joe Vader. He's the candidate who supports the ban. Of those who agreed on the smoking ban, only 80% voted for him. So maybe Joe Vader had other things he was standing for or not standing for that voters didn't approve of. But of those who agreed with him on the smoking ban, 80% voted for him, 7% didn't vote for him, and 13 were still undecided. And then so on. You could read through the statistics, and I've written them in the tree for you already. But here's what we're looking for. 3 questions. If a person votes for Joe Vader, what's the probability that they support the smoking ban? So how much does voting for Vader rely on that voter's support of the smoking ban? And if the person votes for Vader, what's the probability that they had no opinion about smoking? And then if a person doesn't vote for Vader, what's the probability that they don't support the smoking ban? Well, I'm going to try this first one, and then I'm going to leave the other 2 for you. I'll give you a little bit of guideline on it so that you can check your responses. But what we'd have here is the probability of supporting the legislation and voting for Vader divided by those who voted for Vader. So those who supported and voted for Vader, that looks like the 0.62 times the 0.80. So 0.62 times 0.849 or 0.496. Divided by the sum of approved the legislation and voted for Vader, didn't approve, but still voted for Vader anyhow, didn't care about the smoking ban one way or another, no opinion, and still voted for Vader. When we add those up, it should come, so this is part A, when we add those up, that should come to 0.496 over 0.5854, or 0.85, 85%. So do you see that the 85% of if we know that they voted for Vader, then there's an 85% chance that they're voting. What's the probability that they supported the smoking ban? 85%. For part B, let me just give you a little bit of hint here so you could try the example, but then check that you're getting this intermittent step correctly. 0.0144 over 0.5854 when we add up the denominators. And then for part C, we're going to have 0.156 over 0.2218. Well, I hope that this video has helped you practice applying Bayes' formula and has helped you maybe understand how it works just a little bit better. If you do need more clarification on some of those examples that I didn't work fully or need some extra practice, I want to encourage you to reach out to a tutor or contact me, and I'd be happy to help you a little bit more.